Okay, the YouTube stream is live.
Okay, welcome to session A3 for ICALP. We have 6 talks. We have an hour. So our aim is to roughly 10 minutes per talk. They'll give it 2 to 3 minutes quick presentation of their main results, conclusions, and then we'll go to questions. And you can post the questions into chat or post it in Slack, and then we'll turn on your audio. You can say your question when we call on you if you want. So our first speaker is Quan Yang. Quan, do you want to share your screen?
Yes, okay.
Okay, yeah, you can share again. So Quan Yang is his paper is Counting Solutions to Random CNF Formulas. So I'll pass it to him.
Thank you, Eric. So first, let me answer 2 questions on Slack. So the first is that except statistical physics, is there any other sorry, let me. I introduced CNF formula here, and the first question is that except statistical physics, is there any other field that is there other fields making use of the number of solutions to random CNF formulas? So my answer is that there are many fields in combinatorics and computer science that use the number of solutions to the random formulas, because the CNF formula is a good framework and it can capture many problems such as hypergraph independent set, hypergraph coloring. So in the field of approximate counting, we are interested in many counting problems such as counting the number of hypergraph independent set, counting the number of hypergraph coloring. And these problems are related to our work because we can actually the monotone CNF is equivalent to the hypergraph independent set. So we can use the similar method to solve counting hypergraph independent set or counting the number of hypergraph coloring. So that's my answer. And the second question is that at last I mentioned that in our result we require that alpha is less than 2 to the k over 300. This is a big constant because we, however, this is not tight. We do not optimize our result because we do not expect our method can achieve the optimized constant. So we do not improve our constant in our paper. I remember that the tight number by our method is about 100 or 200, but we don't think that's a good improvement. So we do not write the tight bound in our paper. We cannot expect that our method can achieve the optimized bound because we use a local lemma. On page, let me see. Here, during our method, we require that for any variable v, the marginal probability of v is close to a uniform. However, by to obtain this result, we require that the variable on each clause are as many as possible. However, we approximate the number of solutions by approximating the marginal probability of some variables. So we require that the number of variables that we compute is as less as possible. So we require that only a few variables, or only a small fraction of variables that there exists a partial alignment to only a small fraction of these variables that satisfy all good clauses. So there is a constant here. We note that the
Quan, yeah, if I can ask, so just following in this question. So if you wanted to get closer to the threshold,
yeah,
like if you wanted to get closer to 2 to the k, or 2 to the k ln k over k, yeah, one of those, yeah. So would you have to improve? I mean, would you have to allow the non-uniform marginals? Is that the big limitation? Would you have to be able to handle non-uniform marginals? You pointed out that most of the marginals have to be 1/2.
Yeah.
And so if you wanted to get closer to the threshold, do you have to be able to handle the non-uniform marginals? Or, oh, actually there's
actually in our method, we have two parts of requirements. The first part is we hope that the variables in each clause is as many as possible. So the length of clause is as long as possible. And the other part is that we hope there exists a partial alignment to the variables that we compute can satisfy all good clauses. The first part of requirement that says that we can only compute a small fraction of variables. And the second part says that there exists a partial alignment on these variables that satisfy all good clauses. So using Nova's local lemma, we achieve that the alpha is less than 2 to the k over a big constant.
Yeah, you mentioned so you mentioned Lova's local lemma. So there's a question there in the chat from Ji Heng that says, will Shearer's bound help with the constant factor here?
Yeah.
Is that how? Can you help by using?
Here, I think that's maybe a trade-off. If we hope the constant is small, for example, is k over 2.
Yeah.
Then we need to compute many, about roughly half variables. We need to compute the marginal probabilities of about half variables. And then we cannot expect that the variables in some clauses still satisfy our requirements. So the requirement that the marginal probability of some variable is close to the uniform, we cannot satisfy this requirement. So I think here, to improve this bound here, we need some new ideas. I don't think our method here can achieve the optimized bound.
Okay, thank you. Thanks, Juan. I think we'll move on to the next speaker now.
Oh, okay.
Okay, thanks. Okay, Torsten, you want to share
Yes.
your screen? Okay.
I'm
So the
wondering
next,
if I should share the screen or just say verbally. Yes.
Maybe if you share your screen, if you got one of your slides you want to put up.
I mean, I would maybe just jump back and forth in the slides.
Oh yeah, okay. Oh yeah, okay. So whatever you want, it's up to you. Okay, so the next paper is on the central level problems by Torsten.
Yes. Thank you very much. Yes, maybe just to summarize the main results in 2 or 3 minutes. So the main topic of the paper is the n-dimensional hypercube. So this graph has as binary strings, as vertices, all the binary strings of a fixed length n, and you connect them with an edge if they differ in a single bit flip. And n is a parameter, can be arbitrarily large. And what we looked at specifically are Hamilton cycles in this graph. So a cycle that visits every vertex exactly once, and specifically, so this is sometimes called a gray code, a cycle that visits these binary strings, and in every step you just flip a single bit to move to the next one. And specifically, we are interested in subgraphs of the cube. And there's a well-known old problem that is called the middle levels conjecture, which says that if you look at the cube of odd dimension and you partition the vertices into levels according to the Hamming weight. So on a fixed level k, you have all binary strings with a fixed Hamming weight k many ones. And now you do this for the odd cube, and you look at the 2 levels in the middle. So the 2 levels where that have the maximum size, and you look only at the subgraph induced by these 2 middle levels, then this middle levels conjecture says that there's a Hamilton cycle in this subgraph. And the central level problem is a generalization of it, where you not just talk about the middle 2 levels, but about the middle 4 levels or the middle 6 levels, about any even number of levels around the middle, and you want to have a cycle that visits exactly those middle levels. And it interpolates between the middle 2 levels problem and this gray code where you visit everything. And we proved this central levels problem in full generality. So this is the main contribution. And we get an algorithm for it that generates the gray code. So
well, you mentioned the open problem at the end of your slides, actually.
Yes. So
it was about efficiently constructing the Hamilton cycle, right?
Right. So this is one of the open questions. I mean, our proof is constructive, so it gives some algorithm, but the algorithm is not efficient. I mean, depends how you measure efficiency, but if you look at it's polynomial in the size of the graph, but the size of the graph is of course exponential in this parameter n.
Yeah.
And if you want something that is polynomial in n, then this is something that we don't have. So this is an interesting question, if you can have an algorithm that is polynomial in n. And just some simple local rule that just looks at the current vertex and tells you what to flip. And so this we don't have. We have this global construction that looks at the whole graph, but we don't have a local local simple rule that is efficient. Yeah. So this is
What about some of the earlier works, like your result for the middle two levels?
I mean, for the middle two levels, we have an efficient algorithm. Yeah, we have a constant time algorithm even. So that, there we have, in constant time, we know what bit to flip. So this is optimal. And for the full cube, of course, it's also known like the full cube. You have a gray code, like the binary reflected gray code. You can go through the whole cube, and this can also be realized in constant time algorithm. So it's a very simple local rule. And here in the central levels problem, which interpolates between these two, we don't have that.
So the easiest one is that's open is the middle four levels, I guess.
To have an efficient algorithm?
Yeah.
Yes.
Okay.
Yes. Even there we don't have it. Yeah.
Okay.
I was wondering whether you could maybe also say more about the original motivation for the especially the middle levels and the central levels conjecture. Is this purely combinatorial, or are there also some more specific applications that people have in mind there?
I mean, the general broad topic is you want to generate a set of objects efficiently, and one set of objects that is quite popular are combinations. So you have an n-element ground set, and you want to you want to generate all the k-element subsets of this, and this you can encode as a binary string. Yeah, you have an n string of length n with k many ones, and now you want to go through all these and choose k many different strings. And in the middle levels variant, this can be phrased as one particular instance where you want to generate a particular set of combinations with a particular rule, and this is where it comes up. So the middle levels problem can somehow be motivated from different angles, but and this is one of the motivations. And now you can of course ask, why about the middle levels? Why not some other levels? This is also something we do in our paper. Like, we basically prove that you can take any sequence of levels anywhere, and you can have a basically optimal cycle through these levels that you want. The thing about these middle levels is somehow that you have a bipartite graph where both partition classes have the same size, so you can hope for this optimal cycle that visits everything exactly once. And if you start moving around to some other sequences of levels, then you will still have a bipartite graph, but the partition classes will have different sizes, and then you cannot hope for this Hamilton cycle anymore. So this is like a technical condition that prevents this Hamilton cycle. And in those cases, we can prove that you can have something that is as good as you can hope, but not an actual Hamilton cycle. So it's somehow relaxed notion of a Hamilton cycle. I personally like the problem because it interpolates between these classical problems like the mid-levels problem and the classical binary reflected gray code. Now somehow you have all this range in between. This is somehow my personal motivation for this problem. Yeah.
Thanks.
Any other last questions? Anybody? Okay, thank you, Torsten.
Thank you.
Martin?
Yeah, hi. So I have
Hi.
2 slides.
Oh, hi. Yeah, you have a few slides you want to share? The next talk is the complexity of promise SAT on non-Boolean domains.
Okay, so just to remind what this was about, it was about a problem, kind of approximation problem, but with 2 strict versions of satisfaction. So the easiest one was the SAT problem, the promise SAT problem, where we're given a KCNF formula that is G-satisfiable and can at least find a one-satisfying assignment. And this was proved to be NP hard. And we studied an extension of that to non-Boolean domains, to some domain 1 to D. So here's the definition again. The variables that take values in this domain from 1 to D. Literals of the form xi is in some subset of that. Closures are just sets of k literals, and instances are consistent of closures. And again, we ask, given a G-satisfiable instance, is there a one satisfying assignment? So we can think of it as an approximation problem, and we showed that it's usually NP-hard, except for the cases when when your promises are really very strong, then a very simple random walk algorithm works. And just to recall some of the main points about the methods, we use the algebraic framework of Boolean croaking optional. I mean, it's based on a lot of previous work, but that's where it was fleshed out for the promise problems. And we reduced set to a version of a label cover, a promise version of label cover, where we have a label cover problem, and instead of selecting one label from each label set, we select something more abstract on that label set, here specifically polymorphisms on L. So what we have to do is we have to understand those polymorphisms, and here I recall the definition that these are functions of this form with L inputs that map those strongly satisfying tuples to a weakly satisfying tuple. And I've mentioned that if we knew those projections were always, if those polymorphisms were always projections, then this will be the whole reduction, then we will be done at this point. And then there are stronger theorems that says that if those polymorphisms are restricted, that they distinguish some few inputs in some way, then we're also happy. And then in our case, we had to show something even more kind of abstract. We had to look at smug sets, so sets of the inputs, such that the output is equal to the input precisely on those labels, on those inputs. We had to look at those smug sets and the properties of the smug sets, and when you look at that, we realized that we had to prove that this version of label cover is NP-hard. So it's a version of label cover where instead of looking at single constraints, we look at k-chains of arrows. And in the weak version of satisfaction, we only have to satisfy one arrow in every k-chain. And we showed that even this is NP-hard, and this is how we concluded the theorem, so that the problem is NP-hard most of the time. Okay, so are there any questions?
There was a question in the Slack that got copied into the chat. Maybe Martin Kuhneman. Maybe you want to turn on your mic if you're there. Oh, you can ask the question. Oh, yeah, okay.
Sure can. So there was a question by Andrea Torini. She says, you mentioned that the set problem is NP-hard when G over K is below the threshold 1 minus 1 over D by working with smug sets. And based on set solving experience, we know that having to solve an NP-hard problem does not imply that that the solving algorithm is slow in general, but it can be usually very fast, except for few input cases. From a practical perspective, how much difficult do you think the set problem is? And do you think that fast set solving algorithms can be developed?
So I think if a problem like this of this form would appear in practice, then indeed it would be easier. Like the algorithm for the positive case here, where we know an algorithm exists, that's basically walk-set. That's known as walk-set, and it's one of the main approaches to actually solve set instances in practice, even when the theoretical guarantee doesn't work. It turns out to work pretty well, so I expect it would work here as well. And also, as we strengthen the promise gets stronger and stronger, and the problem becomes easier and easier. And it's only proving hardness that becomes harder and harder. So for that reason, also we expect things to become easier. In other words, we have to come up with really tangled gadgets to show hardness. So probably in practice, the problem would become much easier. On the other hand, I don't expect a problem of specifically this form to be very practical. I think we are rarely interested in just the promise of G satisfaction, or in other words, you can think of this problem as distinguishing things that are one satisfiable from those that are not even G satisfiable. So either you get a one satisfying assignment, or at least, well, you don't know if it's satisfiable or not, but at least you know it's not G satisfiable. I don't suspect it's often enough, but I hope that these ideas of reductions, the gadgets that we construct, that might be more useful for all the areas related to hardness of approximation. All this theory of expanders and so on. So gadgets for that are resilient to noise. I think those ideas have more applications than just this algorithmic pack here, and I hope these ideas will be more applicable rather than the algorithm.
Yes, so maybe in this vein, a general questions, are there kind of some kind of the classical hardness of approximation questions where in order to say more about this, we really need to understand this promise CSP type hardness?
So really, the only really very classical problem is this promise coloring problem. Given a k colorable graph, can you at least C color it? So if C more than k colors. And other than that, there's not many natural examples, but it's very tightly connected to the theory of CSPs, and even for exactly solving CSPs, we already see some ideas that are useful for solving exactly CSPs. So it's a very different view on it, and we hope it does help in an indirect way, also with the more classical stuff.
Mm-hmm.
Any other questions? I had a more basic question. So when you show it's in P, you use this Papadimitriou basic random walk algorithm. But there's also for two-set, there's also the very easy graph algorithm, right? Where you look at SCCs in the graph. Is there a graph approach for this, for your thing, or is that related to the LP approach that you mentioned?
So we didn't try actually to get a combinatorial algorithm. We just realized that, well, you can de-randomize it using very general hammers. So
okay.
We ended with that.
Okay. Any other questions? The last talk, it seems to be quite related, I think, right? It talks about the promise problem that you mentioned for colorings, right? Okay, well, thank you.
Thank you.
Nice talk. Okay, I guess we'll move on to the next talk, if there's no other questions. Mina?
Yes.
Oh, yeah, okay, hi.
Great,
You want
hi.
to share your screen?
Yeah, I have a few slides, yes.
Okay.
Just a second.
So the next talk is conditionally optimal approximation algorithms for the girth of a directed graph.
Yes, thank you. Hi, everyone. I'm going to give a very short introduction to the problem. So this is a joint work with Virginia Vasilevska-Williams. Okay, so let's quickly define the problem. The girth is the length of the shortest cycle in the graph. For example, here in this subgraph, in this graph, the red subgraph is the shortest directed cycle in this graph, and the girth is 4. So for the exact computation of the girth, most algorithms just use all pairs shortest paths. And so you can solve this problem in order tilde of mn time, where n is the number of nodes of the graph, m is the number of edges, and order tilde neglects subpolynomial factors. And if your edge weights are at most m, then you can use fast matrix multiplication and solve this problem in order mn to the omega. And omega is the exponent of fast matrix multiplication, and it is less than 2.373. The thing is that both of these results are actually tight under different fine-grained hypotheses. So we move on to approximation results. And for the directed case, the first approximation result was due to Zwick. He gave 1 plus epsilon approximation algorithm for all pairs shortest paths in order n to the omega log m time. But what we are interested in is running times of the form order mn to the 1 minus delta for some constant delta. So the first algorithm of this form was due to Petrocchi et al. They showed a polylog approximation algorithm in order m time, where m is the number of edges. And then just recently, Chechik et al. Showed a order k log k approximation algorithm in order m to the 1 plus 1 over k time. And the best constant factor approximation they get is 3, which runs in order m root n. And so what we do is we first improve this running time, this approximation factor. We show a 2 approximation algorithm that runs in order n to the 3/4 time for unweighted graphs. And we show that this approximation factor is tight. So you cannot go beyond 2. And then we extend this result to weighted graphs. We show a 2 plus epsilon approximation algorithm, which runs in order m root n time. And then we generalize it to 2k plus epsilon approximation algorithm, which runs in mn to the alpha k time, where alpha k is the unique positive solution to this equation that you see here. And just to note that the asymptotic bounds that we get for the general case are basically the same as Chechik et al. We just shave some constant factors, and the main improvements are basically in small constant factor approximations. And another thing to note is that these algorithms all can be used to have round trip spanners. Yeah, so this is all I wanted to say. Any questions?
While you have the upper bounds there, can you remind us what the lower bounds were? How they compare to the upper bounds?
So, well, the lower bound is only for 2 that we have.
Mm-hmm.
And it is from K-cycle hypotheses. And that's the only lower bound that there is for this. So like basically there's no lower bound for the general case.
Oh, okay. And what's the lower bound for the 2 approximation?
So it basically says that you cannot get any algorithm any like 2 minus epsilon approximation algorithm, which runs in better than m squared time.
Oh, okay. Okay.
So there's a question that Thor Oswald wrote also in the Slack, but he's also here, so I guess he can ask this.
If the technology works, I'm happy to ask it. So I admit I haven't thought this through because I'm not quite sure I understand the connection between girth and round trip distance. But there is a paper from a few years back by Virginia and others that gives lower bounds on the round trip distance in terms of the tree width of the graph. And I wonder whether you can prove something like that. So something like n times some exponential function in maybe the square of the tree width. But this may be stupid. I haven't thought this through.
No, it totally makes sense. You said like an algorithm using tree width, right?
Both questions make sense, right? Is there an algorithm that does this, and is there a lower bound under, say, SETH?
Yeah. I mean, yeah, like both of them seem like very connected, basically. Especially that like from the girth results you can get round trip spanners, but we've actually thought a little bit on like if like these techniques actually can be used for round trip distance. And well, we were not like very successful in that, but like that's like I think like it should have like a connection, because like these 2 problems are actually really connected.
Yeah, I'm not even sure. So the difference is that in the round trip distance, you don't require the path back to not intersect the path. I mean, the UV path and the VU path don't have to be disjoint, which they have to be in the girth definition, right?
Well, yeah, that's right. But still, like you have cycles that are going through each vertex.
Yeah, and for the lower bounds, I could easily, yeah, okay. Yeah, I haven't thought this through. Okay, yeah, thanks for your answer. Thanks for an inspiring talk.
You're welcome.
So I maybe have an additional question. So have you thought about proving also lower bounds for larger constant factor approximations? So for less than 2, you rule out these m² running times. So what about can you say something for larger approximation factors?
So, well, the thing is that we don't know what problem to use for those lower bounds. Like the K-cycle hypothesis basically really just like can be used for 2. And like, I think if we want to like prove lower bounds for other approximation factors, we need like another hypothesis. So yeah, I think the main problem is like we don't know like what we can reduce to.
And what's your feeling about your current running time for a factor 2 approximation? Do you think that this could be strengthened further, or do you see a fundamental obstacle there?
Well, so like for the weighted case, we have like a roughly 2 approximation factor in order m root n time, which like kind of seems optimal. So maybe like the mn to the 3/4 running time can be reduced to m root n. But like for the general case, so like if you look at maybe the Chechik's result like gives a better feeling of how these bounds are. So like they have a k log k approximation algorithm which runs in m to the 1 + 1 over k time, and the feeling is that like if you want to spend m to the 1 + 1 over k time, you probably really can have an order k approximation factor, and then log k is not necessary. But yeah, still it's not clear like how to shave that off, because we also have that log k factor in our bounds too.
Thank you.
Any further questions? Okay, thank you for the nice talk.
Thank you.
Let's move on to the next talk, Laureen.
Okay, I have a few slides.
Okay. Yeah, go ahead and try to share your screen. So the next talk is medians in median graphs and their cube complexes in linear time.
Yeah, sorry. Okay.
Okay.
So this is an introduction of the article of ICALP. That is a joint work with Jérémy Chalopin, Victor Chepoy, and Yann Vaxès. So that compute the median sets in median graphs and in their L1 cube complexes. Here I will only describe the terms of the title, like median sets, median graphs, and L1 cube complexes. Okay. So the median set is a set of vertices that, given a positive weight function on the vertices, minimize the weighted sum of the distance to all of the vertices in the graph. And we work with median graphs, which are the graph for which for each triplet in the graph, there is only one vertex that lay on the shortest path between each pair of vertices. So here is an example of a median graph. As you can see, it can be seen as a hypercube glued on smaller hypercubes. The median graphs are really important in many areas, like for example the metric graph theory, like here. Also the concurrence theory, and also the geometric group theory. Because if you replace each hypercube by a solid unit cube, and you underweight in the L2 metric, you get exactly the cat0 complexes. Here we won't do that, but we underweight in the L1 metric, and we work with the and we get the L1 complexes that we will work with. Okay, So the main result is for each median graph, the computation of the median sets in linear time, and also in the L1 cube complexes, the computation of in the L1 cube complexes, sorry, of the median graphs, the computation of the median set in linear time. Yeah. So thank you for listening. And if you have any question.
Any questions, anybody?
Yeah, I might have a question. So my impression from the techniques of your talk is that it's very specific to the median graphs.
Yeah.
So I was wondering whether there's any hope to use some of these ideas also to compute median sets in somewhat more general graph classes if you relax the condition of being a median graph somewhat.
Actually, we don't have any good intuition. Well, we used to have some good intuition, but like allowing the bipartite complete graph K23, but actually we don't have any idea on how we can extend it. Since we use the theta classes, which is not the computation of the theta classes in linear time is not really efficient in many graph types, so we don't have we don't have any good intuition for now.
Thanks.
I have a more basic question. So you're given a median graph, and then you're finding the median set. But how long does it take to test whether a graph is a median graph?
It can be done in I don't have the it's a little it's a little higher of quadratic time, the test.
Okay.
I can do it on the well, I can do the proof, but for example, just to see that it can be done in polynomial time. Since with this definition, you can easily.
Yeah. Okay. But it's not linear time. It takes longer than linear. Okay.
Yeah, it's difficult because we don't have proof yet that it can't be done in linear time. But if we can detect if a graph is median, then we can detect the graph. We can detect if a graph is without a triangle or not. Is without a cycle of length 3.
Oh.
There is a reduction
from detecting whether from triangle-free graphs to detecting whether a graph is triangle-free to
yes.
median. Okay. And is there some analogous problem to finding this median set for triangle-free graphs? Not sure what it would mean.
That's a good idea.
I don't know what it would mean. I don't know. Okay. Okay.
But I.
Any further questions? Okay, thank you for the nice talk.
Thanks.
Okay, so we'll move on to the last talk. Sai.
A few slides, let me
Okay,
share.
Okay, yeah, go ahead, share your screen. Go ahead, Sharon. So the last talk is D to 1 hardness of coloring 3 colorable graphs with order 1 colors.
So this work is about approximate graph coloring. In the approximate graph coloring problem, you can view the problem as a decision version as follows. So given a graph G, and you need to distinguish between two cases. In the first case, the graph is 3 colorable, or the graph cannot be colored with C greater than 3 colors. So for example, if just C equal to 3, this is the standard graph coloring 3 coloring problem, where given a graph, you have to find whether it's 3 colorable or not. But the problem 3 coloring is standard and complete. But the problem gets interesting for larger C. So for example, like can C equal to 4, or even like C, it's even interesting for something like C equal to logging. And there are algorithms that can solve this problem but only for very large C, like n to the 0.2 or something. But on the hardness side, we don't really know much. And even for C equal to 6, it's still open to prove NP hardness. So people are interested in proving conditional results for this problem. So assuming some form of unique M conjecture or some variants, they get results. And our work is also continuation along that line. We prove that D to 1 conjecture implies hardness of 3 versus C coloring for any C and any D. Previously, it's known assuming 2 to 1 conjecture for the 4 versus C problem, where you have to distinguish 4 colorable versus C colorable. So our result is that instead of just 2 to 1, any D to 1 is sufficient. And our hope is that somehow D to 1 conjecture might be easier to prove. And thus, using that, we could solve the approximate graph coloring problem. Coming to techniques, we use the same technique as Dinur Mosel gave of label cover long code based reduction with analytical tools using the invariance principle based tools. But the key difference is that we need to construct a certain symmetric Markov chain with some properties. And that's where that's the novel contribution of our work. And for that, we use matrix scaling to construct this Markov chain. Matrix scaling is a method where given a symmetric matrix, you multiply rows and columns by constants, and you repeat this process to get a doubly stochastic matrix. We apply this procedure on a starting matrix, and that's the high-level picture of our work. If you have any questions, ask them now.
I have one technical. Just so
Right.
you try to construct this Markov chain, this symmetric Markov chain.
Yeah.
And then one of the properties you said you needed is the largest eigenvalue is strictly less than 1, right?
The absolute value, yeah.
The absolute value of the largest.
Oh,
the
it's
spectral radius.
actually, yeah.
I mean, you must have that the largest must be less than 1 too, I guess, right?
Yeah, true. But
so that means it's not ergodic Markov chain, I guess. So there's no station.
No, it's not a strong requirement. So usually we say it's like a bounded away from 1, right? There's no such. Here it's just it shouldn't be equal to 1. That's it.
But then that means there's no stationary distribution, right? So it must not be ergodic, right? Is that right? Or so it's like reducible. It's not irreducible. Is that what's happening?
Yeah. We only need the very basic reducibility property. Yeah, it's not.
So in the end, it must be reducible or something, or it's not connected or something. I mean.
Yeah, it's not connected. The requirement translates to that. It is connected. Sorry, yeah.
It is connected.
It should not be disconnected. Yeah.
Oh, okay.
And it shouldn't be bipartite. Like, if you think of like a graph perspective.
It should be it should be aperiodic. Right?
Yeah, aperiodic. Yeah.
Okay. There's a question in the Slack, maybe from Kusha at Islami. Martin, you want to read it, maybe?
Sure, yeah. So this question is like, to first make it short, it's the question of whether you can use the information of a k+1 coloring to get a k coloring in this promise setting. So
right, yeah. So I've read the question. It's I believe it's probably hard, but I don't know if there is an easy way to somehow prove that problem is NP hard. Because if there is a way to use k+1 coloring to get k coloring, you can obviously recursively use it to get all the way down. Like you can just start with some n to the 0.2 coloring and then keep going. Oh, this everything is for assuming that underlying graph is 3-colorable. So at some point, the recursive procedure has to break if we believe that D21 is true or any of these conjectures is true. But it's not clear where it breaks. So it's still possible that for larger, for C super constant, that might be, that approach helps to get from k+1 to k. But when C is constant, then that problem is hard. But I don't know if there is a way to prove it directly. It seems like a tricky question to prove, because you need to somehow argue that even if you have the k+1 coloring, still you cannot use it somehow. So it's a rather tricky question, I feel, but it's I think worthwhile question, because it is hard, and since 3 versus C is hard, so we do believe it's hard, but I don't really have any way to prove it.
And Marcin has a question also.
Yeah, so I wanted to ask about the D21 conjecture. So the
Right.
2-to-1 conjecture was recently proved for the case of imperfect completeness, right?
Yeah.
So I was wondering, and the proof is quite long. It's remarkable, spread over many papers. And I wonder, do you know if the proof gets simpler for the D21 conjecture with imperfect completeness?
I actually don't know. It's not clear. But that's a good question, whether we can somehow simplify those techniques. We haven't thought through. It seems like their method directly gives I personally am not sure if really hierarchy gives any advantage with respect to their method. But in general, there could be an easier way to prove it.
Okay, thanks.
Yeah, it's a really good question.
And Jakob also has a question.
Yeah, hi.
Hi. Yeah.
So my question is somewhat relevant with a question that Marvin asked in Martin's talk, and namely, can you reverse your argument to get conditional hardness of D21 conjecture from, given that approximate graph coloring is hard? Have you thought about it?
Oh, no, we haven't thought about it. It's D21 might be rather tricky, but D21 is a very special form of label curve conjecture. It's a very special form of label curve instance, right? So I believe one intermediate step could be proving some form of label cover is hard, assuming graph coloring is hard. Even that we don't really know. So I believe if you can first do that, then go to D21 might be the way. Prove that even some form of parallel repetition based result that you get after parallel repetition, like the basic label cover hardness result, even that can you prove assuming approximate graph coloring is hard?
Well, I mean, yeah, of course,
of course, it's true that both are NP hard, but there's if there is a direct way to, without using parallel repetition theorem.
Yeah, you can prove some hardness of label cover, right? The question is whether you can change that version of hardness to whatever version you need.
Yeah, but what I was trying to say is you haven't really used 3 coloring, right, in that reduction. You just said label cover is already known to be NP hard, so is there, but can you somehow specifically use this problem? So I mean, in a way, the question is you're not trying to prove D21 conjecture, right? You're trying to somehow use the coloring itself. but I really don't know how to use this first.
Okay. Yeah.
So let me just end this by, so your question is whether 3 versus C coloring hardness can be used to prove some form of label cover hardness, some easy proof without going through, not the way you asked, but this is an easier version of it.
Yeah. So basically, I'm asking whether you thought about bringing the hardness the other way around.
Yeah, other way. Yeah, we haven't thought. It's a really interesting action, but as I mentioned, like there are all these intermediate steps which are, I think, like worth exploring before going to D21 itself. D21 might be really hard to prove. Yeah.
Okay. Thanks.
Yeah. Thanks.
Any other questions for Sai? Actually, we have a few minutes, so we can change from D to 1 to D to 6 if anybody has questions for any of the other speakers from the session. You're welcome to ask. You can just turn on your mic or put it in the chat and we'll read it.
Maybe just a general comment. Thank you all for doing this. I know reading the room and getting feedback is super frustrating when you just give a talk or basically sit in your living room and do this, but I got a lot out of both the presentations that I could stream and the brief summaries here. And yeah, I thought this was super. Thanks to all speakers for participating in this. It's weird, but it actually works better than I thought.
Yeah, it was great. Yeah, you guys did a great job with the talks were great and the Q&A helpful. Okay, well, thank you, speakers. See you all later.
Thank you.
Thanks.
Thanks.